a smartphone unlocking with your face, an electric car balancing power and safety in milliseconds, a laptop compiling code, and an AI server translating languages in real time. Different machines, same hidden engine, the microchip. Inside each one is a dense city of structures, so small that human hair looks like a suspension bridge by comparison. And yet, these tiny patterns decide how fast your apps run, how efficiently batteries last, and how intelligently machines can learn. The question is almost unbelievable. How do we manufacture something measured in nanometers, layer by layer, without losing accuracy? The journey begins far from the clean room, with a common element pulled from the earth. Then it moves into factories where air is filtered to near perfection, light is shaped into the finest tool ever built, and matter is engineered into the modern world's most precise product. Silicon starts as ordinary mineral, silica locked inside rock and sand. In industrial furnaces, oxygen is stripped away and silicon is refined. But refined isn't enough. For microchips, the material must be nearly perfect, impurities measured in parts per billion. Through chemical purification, silicon becomes ultra-clean polysilicon, ready to be turned into a single crystal. In a towering chamber, a seed crystal touches molten silicon and slowly rises, rotating as atoms align into one continuous lattice. The result is a cylindrical ingot, smooth, heavy, and astonishingly uniform. That crystal is then sliced into wafers so thin they flex slightly, each one a future platform for billions of devices. Edges are shaped, surfaces are cleaned, and the wafer becomes a blank stage where every atom's placement matters. Before any circuits exist, the foundation is engineered for absolute consistency. Now the wafer enters the clean room, a place designed to defeat dust, vibration, and randomness. Engineers move through bright corridors in full-body suits, not for their own protection, but to protect the wafer from a single stray particle. Air flows in controlled currents through dense filters, constantly sweeping contaminants away. At this stage, the wafer is polished until it becomes a mirror, flat on a scale so extreme that even tiny height variations could distort the patterns built later. Chemical baths strip away residues. Ultra-pure water rinses with surgical precision. Under inspection tools, the surface looks like a silent, perfect plane. Yet it's the most important canvas in modern engineering. Because the next steps won't simply print a design, they will carve reality at the nanoscale, repeating the same operations across the wafer with almost impossible accuracy, again and again, until a complex processor begins to emerge. To build a chip, manufacturers don't sculpt everything at once. They create it through repeated cycles of patterning. The signature step is photolithography. First, the wafer is coated with photoresist, a light-sensitive film spread so evenly it looks liquid, then freezes into a uniform layer. The wafer slides into a lithography scanner where optics align it with extreme precision. Instead of visible light, advanced systems use extreme ultraviolet EUV wavelengths, so short they can draw features far smaller than traditional methods. A patterned mask shapes the light, and that light changes the photoresist chemically in microscopic regions. In the developer, the altered resist dissolves, revealing a crisp stencil of the circuit. Zoom in, and the lines become structures only a few dozen atoms wide, repeated across the wafer like a synchronized metropolis. This is how millions, then billions, of transistor elements begin as light, alignment, and chemistry. With patterns defined, the wafer enters the phase where transistors are actually built. Thin films of materials are deposited, some conductive, some insulating, some semiconducting, each only nanometers thick. Plasma etching then removes exposed areas like a controlled sandstorm, carving trenches and gates with sharp edges. Ion implantation adds dopant atoms to precisely change how silicon conducts electricity, creating regions that will become the transistor's source and drain. Layer by layer, the chip rises in complexity. Gates that control current, insulating barriers that prevent leakage, and metal interconnects that link billions of switches into functioning logic. When the structures are complete, the wafer is tested, then diced into individual dies by robotic cutters. Each chip is electrically probed, inspected under powerful microscopes and packaged, wire-bonded or connected by microscopic bumps, into a rugged component ready for the world. From silicon to system, this is precision turned into intelligence, and the future keeps pushing smaller, faster, and more efficient.